Hey young scholar, I'm starting afresh with a fresh new video on a fresh new day. Too much of freshness? Actually, freshness reminds me of fresh mornings and football. The team, the pitch, the goalpost, and our best friends, the training cones. Unlike the stubborn cones on the road, these cones are so amazing. Just standing there, hanging around with their buddies as we jump over them or we dribble past them. These cones actually bring out the best in us. So we must try to understand them better so that we can actually befriend them. But how do we understand a cone better? By understanding its different parts, its surface area and its volume. I'm sorry for beating around the bush. I actually wanted to teach you about cones, but then using examples of birthday caps and ice cream cones is too common. And I wanted to go the extra mile only for you. So, without further delay, let's begin to understand cones better. We have all seen cones at some point or the other in our lives, so we know what they look like. But how are cones formed? Well, in some of our previous videos, we took some 2D shapes and then extended them perpendicularly to form some 3D shapes like cuboids, cubes, and even right circular cylinders. So, is there a 2D shape that can be extended perpendicularly to form a cone? Well, if you remember, we have already discussed that such a 2D shape does not exist. Because if a 2D shape is extended perpendicularly to form a 3D shape, then its cross-section parallel to the base must be uniform, as is evident in the case of this cuboid, cube, and even this cylinder. But if we take a cone and then cut it the same way, we can see that the area of cross-section is not uniform. So the question remains unanswered. How do we really form a cone? Well, one way of forming a cone is by taking a right triangle and then rotating it about its perpendicular side, something like this. Pretty interesting, isn't it? Now, this isn't a random cone. It is special, just like you. It has a special name, which I'll tell you in just a minute. For now, let's focus on this point right here. This is called the vertex of a cone. Now, if you remember, we have studied in our previous class that a vertex is where three edges meet. But no three edges meet here. So how is this a vertex? Well, it doesn't exactly fit the definition, but it is common practice to still call this point the vertex of a cone. Now, to avoid confusion, you can choose to call it the apex. For a cone, the apex and the vertex mean one and the same thing. They are both referring to this point where the surface of the cone ends. Now, the line joining the apex and the center of the base is called the axis of the cone. The axis and the base play vital roles in defining the nature of the cone. I told you that this cone has a special name. It is actually called a right circular cone. Right because the axis is at a right angle to the base, and circular because the base is a circular disc. Now, there can be a cone whose axis is at a right angle to the base, but the base is not circular. And there can be a cone where the base is circular, but the axis is not at a right angle to the base. Hence, neither of these is a right circular cone. Luckily, in this chapter, we'll be discussing only right circular cones. So, in a right circular cone, the length of the axis from the apex to the center of the base represents the height of the cone, and it is usually denoted by h. Now, the radius of the base represents the radius of the cone, and it is usually denoted by r. And the line segment joining the apex and any point on the circular edge of the base is called the slant height. So, this line segment, even this line segment represents the slant height of this cone. The slant height of a cone is usually denoted by L. Now, if you think about it, aren't these just the different sides of the right triangle we rotated? They really are, right? So, using Pythagoras theorem over here, we have L squared is equal to R squared plus H squared, or L is equal to root over R squared plus H squared. This is actually a relation between the slant height, the radius, and the height of a right circular cone. From this relation, it follows that we can determine any one of L, R, and H if the remaining two are given. So, now that we are familiar with the basic terms of a right circular cone, let's use them to understand how to find its surface area. Now, what is the surface of a right circular cone made of? This circular base and this curved surface, right? So, the total surface area of this right circular cone would just be the sum of the areas of this circular base and this curved surface. Now, finding the area of the circular base is a piece of cake. The radius is taken as r, so the area of the base would just be pi r squared. But how do we find the area of this curved surface? I actually want you to employ your imagination for this one. Well, what would happen if we cut open this curved surface along its slant height? We'll get a shape like this, right? Now, if you notice, this is actually a part of a circular disc. It's called a sector, and in future you will be able to find its area directly by using a formula that you will be learning in your higher classes. But what now? Well, we do not have such a formula up our sleeve, but we do have our imagination. Say, this sector is being divided into much smaller sectors such that the arc of each sector, which is basically this part, does not look curved anymore and resembles a line segment. Then, each of these sectors resembles a triangle, right? So, let's name the bases of these triangles B1, B2, B3, B4, and so on. Now, looking at this triangle, what do you think would be its height? Well, we cut open the curved surface along its slant height. So, the height of this triangle, and in fact each of these triangles, would be the same as the slant height of the right circular cone, which is taken as L here. We know that the area of a triangle can be very easily calculated using half into base into height. So, using this formula, the area of this triangle would be half into B1 into L. That of this triangle would be half into B2 into L. That of this triangle would be half into B3 into L, and so on. So now, adding all these areas up, we would get half into B1 into L plus half into B2 into L plus half into B3 into L, and so on. So, if we just take half L common here, we would finally arrive at half into L into B1 plus B2 plus B3, and so on. Now the question is, what would the sum of the bases give us? Well, if you think about it, all these bases together form the arc of the parent sector, and the length of the arc of the parent sector, as you can see, is nothing but the circumference of this circle. So basically, the sum of all the bases would be the same as the circumference of this circle. Now, it's evident that the radius of this circle would be the same as that of the circular base. So, if the radius of the circular base is taken as r, then that of this circle would also be r. So, its circumference would be 2 pi r. So, summarizing, the sum of all the bases would be 2 pi r. Then, substituting the value of the sum of the bases, we get half L into 2 pi r. 2 obviously gets divided and we finally arrive at pi r L. So, the area of this sector, which is nothing but the curved surface area of the right circular cone, is given by pi RL. And if we just add this area to the area of the circular base, we would get the total surface area as pi r squared plus pi RL. Now, if we just take pi r common, we finally arrive at pi r into r plus L. So remember, the curved surface area of a right circular cone is given by pi RL and its total surface area is given by pi r into r plus L. Here, r is the radius of the cone and L is its slant height. Whoa, that wasn't simple. But I'm sure you had fun visualizing the cone being cut open and then being divided into smaller sectors. Mathematics seems difficult, but if you can visualize it, you can simplify it. And if you can simplify it, you can apply it. You know where this is going, don't you? We'll be solving some interesting problems based on what we learned today in the next video. So, watch this quick summary and catch me in the next one. And don't forget to say hi to our cone buddies the next time you go playing. So, in this video, we tried to understand cones better so we can befriend them. We saw that the point where the surface of the cone ends is called its vertex or its apex. The line segment joining the apex and the center of the base is called the axis of the cone. In a right circular cone, the axis is at a right angle to the base and the base is circular. The length of the axis of a right circular cone represents the height of the cone. It is usually denoted by h. The radius of the base represents the radius of the cone and is usually denoted by r. The length of the line segment joining the apex and any point on the circular edge of the base represents the slant height of the cone, and the slant height is usually denoted by L. In a right circular cone, the slant height L, the radius r, and the height h are related such that L is equal to root over r squared plus h squared. The curved surface area of a right circular cone is calculated using pi RL and its total surface area is calculated using pi r into r plus L. Here, r is the radius of the cone and L is its slant height.